Hello everyone, and welcome to our first online concept video. This is pretty exciting. Please give me feedback as to how you like these things. I think you'll like them because you're able to stop them and play them back as often as you like, unlike a live lecture. So let's see how this goes. So the intent for today is to provide an overview of mechatronics that will guide our discussion of sensors and actuators. So the first thing we're going to do is take a look at a mechatronics overview. Again, because this provides us with the context for our study of sensors and actuators. We'll move on then to some examples of sensors and actuators in mechatronic systems, and then discuss how a measurement system is somewhat different than a mechatronic system and how it's similar. And then I'd like to point you into some directions for further exploration. First of all, let's start with definitions of mechatronics, and rather than discussing this for me to discuss that, I'm going to have you explore that on your own. If you go to the author's website, I've put a link into that in your handout. If you go to Internet Link 1.1, that will give you a lot of definitions. So rather than me writing one of them down here, I'm going to refer you to that. Again, don't forget we have a quiz, so this is material you're responsible for on the quiz. But one of the things you'll see in most of the definitions is either the word multidisciplinary or interdisciplinary. And this is because you'll see that there are many different areas, engineering disciplinary areas that overlap to form this central area of mechatronics. So those of you who are mechanical engineers have a pretty good understanding of mechanical systems. Electrical engineers have a good understanding of electronic systems. Control engineers, and there are such things as control engineers, have a knowledge of control systems. And computer scientists or computer engineers understand how to program computers. Computer engineers understand computer architecture. And so what you'll see that these areas overlap with each other. For example, electronics and control systems overlap to create control electronics. We have electromechanics when electronic systems overlap with mechanical systems, and so on. And so where all four of these areas come together form this central area of mechatronics. Okay, so the point here is that it's an interdisciplinary area, and that there are a lot of application areas. There are materials processing. You see that quite a bit in manufacturing plants when we have to pack materials in boxes. We have to physically pack this have this mechanism that packs boxes, but we control it electronically and by computers. We'll see a little bit later an automotive application, and you see all these other application areas around the perimeter. This figure is taken from your textbook, and this basically describes the mechatronic system model. Your author discusses it. What I'd like to mainly highlight is basically what we're trying to do is we're trying to take a mechanical system and control it with some kind of a computer, microcontroller, some kind of intelligence, or some kind of automation. And so everything besides these two blocks is meant to support those two main components. So we have the brain that's trying to control some device. So what allows us to do that are sensors and actuators. And I would actually take this little arrow out here. So basically what happens is that in order for the computer to control the device, we have to first sense its state. Whether we might be trying to determine its position, its speed, its temperature, some kind of energy we might be trying to measure. Whatever it is we're trying to measure, we need to sense that. And so what the sensor does is it takes some physical quantity, whether it's speed, acceleration, position, temperature, etc., and it converts it to an electrical signal. From there, the electrical signal needs to be converted into a form that our controller can use. Now, if we're using operational amplifiers, which are analog devices, we might only need to maybe perhaps amplify the signal. Okay, so amplifier is a kind of signal conditioning. If, however, we're going to feed it to a digital computer or a microcontroller, then we also need to convert the analog into digital, and that's what the A to D stands for. Then once the digital signal is brought in, we can create some kind of algorithm, and usually that's done with some kind of program. So control algorithms, or we might do it with some kind of a programmable logic device. And then we need to sequence and time the various operations. Now, once the computer has made a decision based on the state of the system, is it doing what it's supposed to? What adjustments need to be made? Then we need to tell the system what state to assume. And that happens through this leftmost loop. So first of all, basically, we talk to the device through actuators. So we might have a motor that turns a shaft that will change the position of some antenna, for example. We might have a hydraulic piston, the cars, when you take your car for repair and they lift it, that's a hydraulic piston that it raises up and down on. So there needs to be something that changes the state of the mechanical system, and that is the actuator. And so we have some kind of electrical signal that drives the actuator. And again, the actuator, the output of the actuator is some kind of mechanical energy, usually. And so what happens here is that the controller puts out a digital signal, and then this digital signal is usually converted to some kind of analog signal that is in the form needed to turn on the actuator. And then as an adjunct, you can also have graphical displays that display to the user what the status of the system is. But the main blocks, again, are the brain and the device. And then on the sensor side, we're trying to get the signal into a form that the brain can understand. And then the brain has to get its idea across to the mechanical system. So that's basically the model.